Hello, I'm here with Eric Loyd, a PhD candidate in high energy experimental, right?
Yes.
Yeah. At the University of California, Riverside. And the first thing that I want to do is just going to be doing the basic interview question, which is tell me about yourself, tell me about like your background and what type of research you do.
Sure. Yes. So hello, my name is Eric Loyd. And I am a seventh year graduate student here at UCR, so University of California, Riverside. And I guess a little bit about me. I'm currently 31 years old. I'll turn 32 here in August. And like I said, this is my seventh year of graduate school, so I've been at it for quite a while. Um, and I've been interested in particle physics ever since I was very little. So this is kind of, the culmination of sort of a life's journey that has brought me to this point where I've been able to do all this research, and I'm now gearing towards defending my PhD dissertation. Um, and so the type of work that I do specifically in my field of high energy particle physics is I look at quark gluon plasma.
Okay.
Do you know what quark gluon plasma is?
I know what a cork is, and I think a gluon is made out of glue, or that's where the name comes from.
Well, glue is a pretty good way to think
Yeah.
about it. So gluons are the sort of glue that hold nuclei together. So nuclei being protons, neutrons, the more typical atoms. They are held together by the strong force, and the strong force is mediated by the gluon.
Hmm.
So the quark gluon plasma is, to be short about it, is this hot, soupy substance that is made out of quarks and gluons that aren't really attached to each other in any specific way. And uh, in order to get a quark gluon plasma, you have to heat normal everyday things, normal everyday matter to very, very high temperatures.
Okay.
We're talking at least a billion times hotter than the surface of the sun.
Hmm.
So very hot, very difficult to make, and it is thought that quark gluon plasma, fill the early universe in the first micro fractions of a second after the Big Bang. So that's for sure one of the reasons why we want to look at it, because it gives us a window into studying those
Hmm.
early universe conditions. And also because it is more generally just a novel state of matter that we're typically not very familiar with.
Okay.
Um, so uh, my specific project looks at a property of the quark gluon plasma, which we call flow. So the thing about quark gluon plasma is that it behaves like a fluid.
Okay.
Um, we also often call it a perfect fluid because it has a very high, what we call a shear viscosity, which means that it has very little trouble moving about itself.
Okay.
Um, so, uh, so we look at this hydro because it's a fluid, we can apply the principles of hydrodynamics to it. And one of the hydrodynamical variables is this flow.
Okay.
Um, is it hopefully apparent what exactly I mean when I say flow?
This is a conceptual physics class that's gone over a lot of different types of physics, so we might not have specifically said like the specific parameter flow, but we have gone over generally like Bernoulli's equation and uh, fluid dynamics in a lecture or two.
Okay. So it's maybe reasonable that the student might be familiar with like laminar flow or turbulent flow.
Uh, Not at the level of this textbook, but you can just define those terms if you'd like.
Yeah, so these are types of these are like specific types of flow. So like laminar flow, for example, is something that you would find in a very calm river. So, in a calm river, you have all your water and it's just moving steadily downstream, and it's generally a pretty stable flow. There isn't really any turbulence going on. You're not like forming rapids. Everything's just going slow and steady in a straight line. So that's laminar flow. You can kind of sort of see this if you maybe turn on a faucet and if the water comes out and it's, it doesn't really, move about too much.
Yeah.
That's also another example of laminar flow.
Yeah.
Turbulent flow is when the water is starting to churn and twist and race about in some places and slow down in others. So there's really not a good measure. Well, there's not really a clean way to describe how every part of the fluid is moving.
Yeah.
So it is turbulence. You often hear about this. In when you're flying on a plane, you experience turbulence. That's because the air around the plane is moving in unpredictable ways, and it can make the plane move this way or that way. And in ways I mean, planes are designed well, so
Yeah.
they can handle these things, but doesn't make for the smoothest ride.
Okay.
So to put a more explicit definition of flow, it's the measure of how the parts of the fluid move in relation to each other. And so directed flow is is a specific component that we look at. When we make when we collide particles in our collider, they smash together and a fireball is made. And
Okay.
this is going to take on a sort of almond shape that expands. And you can reasonably guess that the bits at the very center of the almond are under intense pressure, and that is going to give you some impart some outwards momentum
Okay.
on the rest of the fireball. It's going to push the rest of it outwards. Maybe towards the outer areas of the fireballs, maybe a little less pressure. So your momentum distribution is also smaller in that region.
Okay.
Um, and so we can look at the shape of this fireball and we can mathematically describe it um, in terms of like, uh, I would presume that students probably know what spherical coordinates are.
This is a conceptual physics class with no algebra base.
All right, so then maybe I'll give a qualitative description of this as well. So, in spherical coordinates, you can measure a point in space um, by some distance that it is from the central point, we'll call it.
Yeah.
So, like if I were to say, oh, what's this up here? Well, it's a point that is this far away, maybe like I don't know, this is a foot away from the central
Yeah.
point, and I'll describe it in terms of two angles. We'll call it the azimuthal angle. First is the azimuthal angle, which is, if you're looking at a circle
Yeah.
and you want to describe an area, a point what the angle is on the whole of that circle. We call
Yeah.
that the azimuthal angle. We also have the polar angle, which is like, how far north or how south you are. So I guess a really good way to illustrate this is how we measure locations on the Earth
Yeah.
with latitude and longitude, where longitude is the azimuthal angle.
Yeah.
So you could be 0 degrees east or 5 degrees west or 135 degrees west. That's how we measure that. And then with latitude, that would be the polar angle. So you could be, I don't know, we're around 35-ish degrees north here in California.
Yeah, I think so. There's that cafe in UCR that's like latitude 37 or something like that.
Okay.
Yeah.
Yeah. And yeah, and these are values that we could look up if we had the time to, but you can also have like 40 degrees south. And so that is exactly how we are measuring the Earth. And we can do a similar thing with the shape of the fire. Now, the thing about the azimuthal angle,
Yeah.
because it's a measurement that goes around the whole circle. you can imagine that if I say at zeros, it's this long. If I go all the way around to 2 pi, I should
Yeah.
get the same value.
Yeah.
So we call this a periodic function. And because it's periodic, we can do a higher order mathematical operation called Fourier expansion. I'll leave this as an exercise to the viewer on
Yeah.
what exactly that entails. But I will say that we look at it is it is a sum,
Yeah.
and there are infinitely many terms to the sum.
Yeah.
I look at the first one. Um, and so there is a symmetry that gets rid of a bunch of them. So you're left with all these cosines. Again, exercise for the viewer on what a cosine is. But I look at the we call it the coefficient in front of the cosine. And depending on what value this takes on, it could be positive or negative in terms of uh, what the radial component of our
Yeah.
measurement is, or what our polar angle is, although we use something slightly different
Yeah.
because this is high energy stuff and relativity comes into play, and
Yeah.
there's all sorts of things we have to do with that. But as a function of those things, we can make a measurement of this coefficient,
Okay.
and that actually tells us a lot about what is happening inside the fireball, including if a quark gluon plasma is being created or not.
Oh, okay.
That's the general field of which I study, and what I particularly look at is I look at this, we call it V1 because it's the
Okay.
first coefficient, also known as directed flow,
Okay.
um, which
Does B stand for speed or velocity, or is it just
that's a good question. It does not really stand for anything at all.
okay?
It's just a symbol that we use.
Okay.
So don't confuse it with velocity in this case. Um, and so I look at V1, which is kind of a measure of where the stuff in the material is collecting as this fireball expands. So, for example, if I have a positive V1 and the fireball is kind of moving in this
Yeah.
direction, if my V1 is positive, the majority of my stuff in the fireball is going to be at this front end.
Okay.
And likewise, if this is negative, everything is going to be at the back and it's going to be sort of pushing the fireball along in some sense.
Okay.
I look at this for protons, which we're all familiar with. I look at them for pions and kaons, which they belong to a more exotic class of particles that we call mesons,
Yeah.
um, which is so a meson is made out of a quark and an antiquark. They come in a pair.
Yeah.
Uh, I'm sure everyone has heard of antimatter, and uh, there's so antimatter is made out of
Yeah.
antibaryons, which is are themselves made out of antiquarks, and then you have baryons, antibaryons, and then in between you got the mesons, which are a little bit of both.
Okay.
So pions and kaons are members of the mesons. And then I look at the antiproton as well. So I look at the baryon and the antibaryon. I look at some heavier versions of the
Okay.
proton. The first of these is called the lambda zero.
Okay.
We call it a lambda zero because it is electrically neutral. There's also the anti-lambda, which is just the lambda zero, except made out of antiquarks instead of quarks. Uh, there's a slightly heavier version called we call it the Cassi. So it's the
Yeah.
Greek letter Cassi, but
Yeah. It's a little squiggly one.
it's not that. That's well, you know what? I don't know what that's. I think that's Zeta.
Or
I
yeah, it doesn't really matter.
Yeah, well,
You
well,
can
well,
Google it.
most people in our field don't even call it the Cassi. We call it the Cascade, which is much easier to say.
Yeah.
We look at the Cascade baryon and the anti-Cascade as well. And finally we try to look at the omega baryon,
Yeah.
which is made out of three, we call them strange quarks, which it
Yeah.
is an actual type of quark. It's the slightly heavier version of the down quark. So omega is three strange quarks, and we can also look at the anti-omega.
Okay.
And from there, we were able to compare the V1 of all these different particles and see if there are any trends that jump out at us.
Yeah, that's a pretty good explanation of your research in particular, and also just like the ideal particles and like the constituent subparticles, I guess,
Hmm.
would be a good term. So, what I'm going to do for this interview is going to be mostly questions from the students are coming up, which were broken up into astronomy, condensed matter, and high energy questions. So I'm going to ask you the high energy questions. And then for all three of the people that I'm going to be interviewing who are currently research scientists, I am going to go through a bit of just personal questions, not really like uh, telling us your deep dark secrets from childhood or something, but just like a few personal questions about what it means to you to be a physicist, uh, so we can get an idea of like how different types of people come into the field.
Hmm.
So the first one that I want to do that's going to be one of the general questions is what's your physics against other areas of study? You said that you enjoyed it from very early on, but what specifically brought you into high energy physics?
Yeah, so the more particular explanation that I had for myself was I was always just very interested in like the most fundamental of the physics. Like if I wanted to study the universe, I wanted to get down to like the very, very nitty-gritty, the most basic of things. And so in my mind, particle physics, that underlies everything because
Yeah,
everything that we interact with is made out of particles. So the matter that the condensed matter
yeah,
experimentalists work with, that is made out of
yeah,
particles. The galaxies that the astronomers study, those are also made out of
yeah.
particles, although considerably a lot more particles than we typically deal with. But yeah, it's way down there. So this work that I do right now in looking at these fundamental properties of normal matter,
Yeah.
it's very superheated, sure, but normal matter, it scratches that
Yeah.
that I don't know if I said the word itch, but my voice kind of cracked there, and I was like, oh, that's not going to get picked up.
Yeah. I hope that this is filtering out background noise because when I was talking to a professor who, or not a professor, a teacher who everyone who's going to be interviewing also knows, I was doing it outside and hopefully it wasn't just drowned out by a bunch of birds. But can you describe the research you have done? You've already done that. I kind of skipped ahead in our little lesson plan. But do you prefer fundamental research, theory, or applied work?
Um, so I think, well, I definitely don't have the mind for theory. I will readily admit that. Um, I think applied work is is not really the answer either. Um, so, like I said, I want to scratch the itch and look at the very most fundamental things and figure out how they work. So, I guess in that sense, I'm not really searching for applications
Okay.
of my research. So, yeah, I guess the answer is I prefer fundamental
Yeah.
research.
Yeah, and I think that's going to be a lot of the reasons that people become physicists rather than becoming engineers is liking that fundamental research.
Yeah.
And then after you've this is a question that's directly from a student. So, after you've worked in your field for as long as you have, would you say the curiosity in some specific areas of your work has increased or decreased? Are there any things that bother you that it's not exactly explained by our current understanding of physics or
Yes.
by how people teach it to us, I guess?
Yeah, so that's a very good question. And I would readily answer that my curiosity has actually increased
Hmm.
since I really got into the thick of this journey. And I would say the reason for that is because I've learned so much since then. I've been made aware of the things that I didn't know before. So it's like, when I was a kid, you don't know what you don't know.
Yeah.
And now that I've gotten into this, I kind of know what I don't know. And so I can more clearly picture where the holes are in our understanding of things and what needs to be done. And it's you know there is still much so left to do.
Okay. Yeah, very Socratic answer.
Hmm.
Only Socrates is the wisest man, for only he knows that he knows nothing,
Right.
which is a good thing to know rather than to be ignorant and proud of it, I believe.
Yeah, and I suppose that's a really good mindset to have with things like this. Um, you want to try to not have an ego with it, um, because we don't know everything. That's just how it is.
Yeah,
And we will be on this journey for the rest of our lives, for generations, most likely. Still no reason to stop though.
yeah,
That's we are the reason we've gotten to where we are today is because of the research of those who came before us, who certainly were in the same position that we're in now.
yeah. The I teaching I've just accumulated a lot of science quotes, but like that Einstein, if he sees farther, it's because he's standing on the shoulder of giants.
Exactly. Exactly.
Yeah. And another question about kind of, I think a lot of the difficulty that students are having as they get into physics is complicated math. So does that get easier for you, or is that still a problem?
Um, so math is like mm, a muscle, I
Yeah.
guess. It's definitely something you have to practice to get good at. And again, I will admit that I might not be the best at math. However, having stuck with this as long as I have, I've certainly acquired a grasp on these things. So I've internalized all the trigonometry that I need, which
Yeah.
it does actually show up quite a bit in our work because we
Yeah.
are doing a lot of geometrical stuff. Um, I've become familiar with Bessel functions, which those are some advanced things, exercise for the
Yeah.
viewer.
Even more complicated Fourier series.
Very complicated things in general, but there is actually a part of my exact project where they do enter, so I've had to use them, and I've had the privilege of not only being able to kind of figure out how to use these things, but to explain to my colleagues how to apply them as well and why they work the way they do.
Okay. Nice. And then what are the biggest unsolved problems in your field right now?
Um,
Part
so
of, yeah.
yeah, no, go ahead.
Or no, part of the reason that I'm having these interviews is because the final project, at least for this semester, is going to be looking at one of the unsolved problems on Wikipedia and writing the connection between the more fundamental physics we have and like how that evolves into the more complex things that we don't know the answer to.
Yeah. So the biggest unsolved problem in the field right now is kind of the same as it's been for a while, which is um, how do we, unify some of our theories for, particles, quantum mechanics does a rather decent, well, not just rather decent, it's a
Yeah,
very darn good theory. But
yeah,
how do we marry that to the theory of the very large, like general relativity?
yep,
We still haven't formulated a unified theory of everything
yeah,
as of yet. So that's one of the things. There are some other things that we've theorized about that we really don't know how to 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 find. So, dark matter is an
yeah,
example, which this I'm sure the astronomers are also working on this, but we don't really have the means to detect dark matter, and we're not even sure what they might be. There are some things we've been managed to rule out,
yeah.
but we don't know how to test for it or how to measure it. There are these things called there's like these things, supersymmetric particles,
Mm,
which um, that's a whole topic in on itself, but we don't know how to test for those either, and there is an increasing pessimism as to whether they even exist or not. String theory is another thing that we can't really test for,
yeah. I've
which I think that's like the closest answer we have to a unifying theory, but
Yeah, but it doesn't make any predictions. So, according to the definition of science that we went over in the first lecture of this class,
yes.
it is not science.
I mean that is a fair definition to have, and I would in fact agree that the best science makes predictions about the world around
Yeah.
us. So I'm no string theorist expert, but if it doesn't make any predictions, then yeah, it's not going to really do much for us. It would be nice if it explains things, sure, but we want that tool behind us as well.
Yeah. Okay. Oh yeah, and impacts. So, no, as I said, most physicists aren't going to care too much about the impact of what they do. They're more in it for the joy of discovery. But what are unexpected impacts that have happened, and what might be impacts in the near future of high energy physics?
Yeah, so this is one of those questions that I don't really have an answer for. This is probably something you maybe approach an engineer about.
Yeah.
So for applications of my work specifically, I have no clue. Um, Something that I am aware of that does kind of come out of particle physics research is the technology of PET scans. So
Hmm.
that uses positrons and electrons to scan people. Make scans of people, very deep probing scans,
Yeah.
which allow us to figure out what is going on the inside of people and maybe diagnose issues.
Yeah.
And if we didn't know what positrons were, we wouldn't be able
Yeah.
to do that.
And I think it is also worth noting that all of the particles we know were initially because of what was considered high energy at the time.
Right.
We just build bigger accelerators to
Yes.
find more interesting particles.
Yes.
Yeah.
The
And
funny thing about that, and we talk about building accelerators all the time, but the question has become, well, if you build an even bigger accelerator, what are you actually going to find? And is a school of people that think you're not really going to find anything new. So do
okay,
you even want to build the bigger accelerator?
maybe. Yeah. And speaking of accelerators, what kind of technology or tools do you use in your research?
So there's quite a bit that goes on with that question. Um, so perhaps I could break down the exact process of how we eventually get all this stuff in our detector. So at the relativistic heavy ion collider, which is where my experiment is located, we have this store of gold nuclei,
Hmm.
and these are going to be gold nuclei with the the protons and neutrons are in the nucleus, and then there are the electrons that are, floating around them.
Mm,
The very first step that we do is we strip all those electrons away, thus uh, uh, ionizing
yeah.
all these gold nuclei. And we can do this using electromagnets. So the technology of electromagnets enters into this at the start. And we can, I think these are superconducting electromagnets as well.
Oh,
So
nice.
that
Yeah.
very definitely helps. And using these magnets, we're able to accelerate these ions first in a linear accelerator. So they go like this. And then as they go faster, you're going to need longer and longer lengths to keep working with this thing. So we start transitioning to rings at this point. And you're still utilizing these electromagnets along the circumference of these rings, and we can go to steadily larger and larger rings as we want to make the particles go faster.
Yeah.
And in fact, if you want the particles to go at really high speeds slash really high energies, you need these big rings like this. So we go to big ring, bigger ring, bigger ring, and then we enter the Large Hadron Collider. That is not even the right collider. That's the one.
You've only been working there for 5 years.
I misspoke. I'm sorry. The Large Hadron Collider is the one in Europe. It's not the one that I work at. I already mentioned the relativistic heavy ion collider, which it is in on Long Island, New York. So, and we call that RIC for short. So our gold nuclei enter RIC and they'll circle around several thousand times a second.
Mm,
Um, and then the star detector, which is where my experiment is, it sits somewhere on the ring. We can focus the gold nuclei to collide with each other,
mm.
and so they'll shoot out and hit our detector. Um, I think I know where I want to go with this question next. What was the question again?
Just what tools you
Yeah,
use.
so we're still talking about the tools.
Yeah.
So we have the detector is there, and we have all these systems to monitor what is going on in the detector. But for the most part, the acquisition of data is automatic. Aside from us telling the detector, "Hey, we're taking data, record all these things," or "Stop taking data, or we're not going to record things for a bit." And so we can collect the data that comes out of our detector, and it goes into this thing called the DAC, which we call the data analysis queue,
Oh,
where we take the raw data that we save in our detector, and we do a little bit of processing on it to get it ready for eventual analysis. And there's a whole process in that, and everyone does it in shifts. So
yeah.
I've worked that detector before. Uh, and so once the data's been collected and processed and released to all the people at STAR, we can then utilize the computer systems that are uh, provided by the laboratory to create our analyses. The um, the favorite, I would say, is Root C++,
Okay.
where C++ is a very common programming language, and then Root is like or Root C++, I should say, is like an interpreter version of C++. Um, and it allows us to do all these calculations, make pretty plots. Um, and so it gives us everything that we need to, analyze the data and eventually present it to our peers. Um, but the one other tool that we also need is vast computing power,
Yeah.
because there is so much data that we collect. For example, in some given collision energy, and Rick takes, or well, Star takes many collision energies. For any given collision energy, we may have several hundred million events, and you're going to have several hundred particles per event. So it adds up very quickly, and you have to look at all of those, or nearly all of those. So we need fast computing resources. So we have what we call Condor,
Okay.
which is basically a collection of machines. I think like several. I don't know if it's several thousand individual machines, but it's like we have several thousand processors where we can put a portion of the analysis in and have it run in
Okay.
parallel with everything else. And that allows us to get these things done really quickly. Um, so yeah, I would think that for the most part, that's all the tools that we need. We need the technology of the collider complex, the technology of the star detector, and the data analysis acquisition methods, ways to analyze the data with root C++ and our large computing resources.
Okay. Yeah. Nice. And then there is a question about electromagnets, but you already went over how you use electromagnets to get in there. And
Yes.
then this is a question that was kind of repeated over and over again. So I'm just going to ask everybody how electromagnetics or electromagnets work in their uh, field. Probably not going to be too much in astronomy, but it's definitely something in high energy and condensed matter physics.
Sure, I can kind of explain this a bit. So, with electromagnets, so the cool thing about electromagnets is that we can turn them on and off
Yeah.
depending on if we supply them with electricity. And so, what ends up happening is that as we strip all the electrons off of the gold nucleus and thus ionizing it, the gold nucleus then has a positive electric charge to it. So that means that it is susceptible to not only electric fields, but also magnetic fields.
Hmm.
And it is the magnetic fields that we use that are provided by these electromagnets that allow us to accelerate
Yeah.
um, these particles. You can think of it as you have your gold nucleus, and it's going to encounter the magnetic field created by an electromagnet. And so something that we learn is that if you have a charged particle moving through a magnetic field, it will accelerate
Hmm.
um, perpendicular to the field,
Yeah.
but it will still accelerate, and we can still make use of that through very careful positioning of all of these electromagnets. We can make the particle go in a straight line,
Yeah.
or we can make it curve, as a matter of fact. And because it is accelerating, changing velocity, we can accumulate enough forward velocity to get it to these really high relativistic speeds where we want these things to be going.
Yeah. Nice. And uh now we are actually going to move on to the questions that were specifically for high energy people. So, one question I have for high energy slash particle physics is in regards to the semi-direct fermion. So it's a quasi-particle which is predicted to have mass in one direction and to be massless in the perpendicular direction. Do you know anything about that? I asked Mr. Baker uh, a few days ago, and he basically just said what the question states.
Yeah, I think I would have to sadly give the same
Yeah.
answer. And this is because these things are outside of my field of study.
Yeah.
So, yeah, I'm afraid I don't really know much about this.
Okay. And then what are the biggest challenges when it comes to energy loss, like heat or radiation, when you're talking about just slamming very small things together? Does the friction in the air cause there to be heat loss in the same way that you would get with the very large things being slammed together?
Um, so with the yeah, that's a rather interesting question because the loss of energy is actually something that we measure to a useful degree in my field of study. So for the most part, we hope that the collider is in vacuum.
Okay.
So how it's set up is that you have these two rings that are one's going clockwise, one's going counterclockwise, and at the points where they intersect, which we make them intersect with some geometry. Um, where was I going with that? Oh
Huh?
my gosh. Um, well, so these rings are in vacuum, and so we don't really have to worry about any of the energy loss inside the beam, other than there is radiation.
Yeah.
Um, and so there is radiation caused by the beams because as charged particles accelerate, they do radiate energy, and that is something that is constantly happening inside of Rick. But we're able to continuously replenish that lost energy thanks to the numerous electromagnets that line the Rick rings.
Eh,
And then in the collision itself, like I mentioned, we can use energy loss constructively. So you smash your stuff together, and it's all going to fly out in all these different directions. And it does have to pass through the detector. And in doing so, it is going to lose energy, but we can measure that. And in fact, we can't, the value of energy loss that we measure allows us to identify what is passing through the detector. So, if, for example, a uh, track, we call these things going through our detectors track.
okay.
If a track is going through the detector at some momentum, which we can also directly measure the momentum
Yeah.
as well, depending on if how curved the track is. If for some momentum we measure this energy loss, we say, oh, this is what I expect a proton to lose at this momentum. So that makes it very likely that this thing that I'm looking at is a proton.
Okay.
We can do that with pions and kaons as well, which are other things that we directly see in our detector. Um, so yeah.
Yeah. Yeah. So there, for some reason, it never occurred to me that they would be in under vacuum. It just seems like how big they are. It seems crazy that you're able to get it under vacuum. But I guess if I used to work with vacuum chambers for condensed matter physics in order to get clean data, I think that it's more important that you work under vacuum.
Right. Yeah, we do not want those, well, what we call secondary
Yeah.
reactions to occur.
Yeah.
Um, Now, it does take a lot of time to set it up and get
Yeah.
it to vacuum and sufficiently cool it down because these aren't simple vacuum chambers. You're
Yeah.
right. These are entire rings that have a circumference of around 4 kilometers. And each ring is like the beam pipe is like this big.
Ooh.
Yeah.
Okay.
Um, and but maybe you'll believe me if that the actual beam of particles and this may not show up well, but it's even less than the distance between my two fingers here. It's really, really small.
Okay.
Because these are atoms. They're always small.
Yeah. Ooh, I just remembered the guy who, this is completely off topic, but the guy who was working on a particle accelerator, like just getting everything working inside the tube, and then they accidentally turned it on and it went straight through his brain and he just kept living like that.
Yep.
Crazy. Couldn't grow hair out at that point anymore, but do not do that. That's going to be my point. And did the laws of conservation of energy and momentum work the same way in cosmic processes as they do in Earth-based systems like hydropower? The cosmic processes kind of implies astronomy, but I thought that that was also a good question for high energy.
Yeah, so the thing about conservation laws is that they work very well. Well, they're always true in what we call a local context. And so that I should put emphasis on local. Um, and I'll explain why in a second as that gets into more an astronomy half of this question. But we there are some momentum conservation effects that we have to take into account when we're doing our analysis. Um, so that is a might get a bit technical. So I think I'll forego
Yeah.
that, but it does enter in some ways. As for cosmic processes, this is where we kind of stop being local. And it might surprise the viewer to know that at very large time scales, uh, things like energy and momentum are not conserved.
Mm.
And the reason for this is because the universe is expanding.
Oh.
Um, so, uh, it's, uh, so if you ask an astronomer, what they will tell you is that the space, the actual bedding on which our universe sits, is expanding. So the distance between two stationary objects, as we see them, is very slowly increasing, and it is increasing at a rate called we call it the Hubble constant,
Yeah.
and that is 70 kilometers per second per megaparsec.
Mm.
Might be worth our while to break that down. So I'm sure everyone knows what a kilometer is. Everyone knows what a second is. What's a megaparsec? Well, a parsec is a unit of length.
Yep.
It's equal to 3.26 light years. So very large length. And then a megaparsec, well, so mega is a prefix that means million. So a megaparsec is 1 million parsecs or
Hmm.
3.26 million light years. And so what 70 kilometers per second per megaparsec tells us is that if there is some object that is a megaparsec away from us, it is going to be moving 70 kilometers per second away from us. If there's some object that is 2 million parsecs away from us, it will be traveling away from us at 140 kilometers per second, so twice the velocity away. And this holds the further and further out you go. And it doesn't matter which direction you look in either. All of its space is expanding away from us. Um, and because there is a loss of this time symmetry, which there is a very intimate relation of symmetries in nature and conservation laws.
Yeah.
The loss of time symmetry means that we also lose these conservation laws across these long time scales.
Yeah. Okay. So I was actually a student of mine actually showed me a Veritasium video that's 30 minutes long and was released about uh 3 week or 4 weeks ago that goes into a lot of detail about this.
I watched that video, and that's actually what I'm kind of referencing here,
Yeah.
as a matter of fact.
Yeah.
I
So
would recommend the viewer to give that a look. It's
yeah.
highly fascinating.
Yeah, I'll add that to one of the playlists on YouTube. And I was uh when I was talking with Mr. Baker a few days ago, I was kind of skeptical about that because I am skeptical a little bit sometimes of pop science videos. But if what you've studied is corresponds to it, then I am going to have to eat my words and say that it is something worth looking into.
Well, I wouldn't say my study corresponds to it per se,
Yeah,
so you might be safe for a while yet.
yeah,
But you could pose this question to Nicole and see
yeah.
what he thinks.
Okay. Yeah. And one of the big questions, and I know that this is very important to your research, is if I could interview with a high energy slash particle physicist, I would ask how they study particles that only exist for short periods of times and how do they analyze this data?
That is such an excellent question. I'm glad I'm being asked it because this is the exact problem that I deal with
Yeah.
as part of my specific project. So, I mentioned in my overview of my research that I look at these heavier versions of the proton. So, the lambda, the cascade, and the omega, plus their anti-particle versions. And that is the exact problem is that lambdas and these other things, they don't live for very long.
Yeah.
In fact, they don't live long enough to move from the fireball into our detector. They decay into smaller things. They do decay into things that we can see, however. So, for example, the lambda baryon, it decays into a proton and a pion pair. And protons and pions are things that we generally see in our detector. Oh, excuse me. Um,
Yeah, we've been at this for a little while.
yeah, that's fine. Um, Same thing with cascades. They decay into a lambda and a pion pair, which that lambda itself will then decay into
Okay.
proton pion. Same thing with omega. That will decay into a proton, or no, a lambda kaon pair,
Hmm.
then the lambda will decay further. But but that is all to say, these things decay into things that we can see in our detector, and we do. But we are able to identify these protons and pions as having come from uh, some area that is, isn't we call well. So there's a thing we call the primary vertex, and that's the point in space where the collision actually happens and the fireball expands outward from.
Okay.
And anything beyond that we call like a secondary vertex. And so we can identify some of these proton pion pairs as, in the case of a lambda, having come from a secondary vertex. And we can do this by, we look at their paths and we see that they intersect at a common point. And based off that, we say, okay, this could be a lambda. We do need to check it. And there are some methods in which we do that. There's this calculation with this thing called invariant mass, which I'm not going to get into, but you merge your proton and your pion together, you're going to get a particle, and it will have some mass associated with it. And if we take that calculation and compare it to what we know is the mass of the lambda, we say, oh, this is a very good match. So very, very good chance that this is a lambda. And we treat it as such.
Okay.
Or this is not so good of a match. It's wildly off what I expect the mass to be. So this is probably not a lambda. And we treat it as such.
Okay.
So using methods exactly like that allow us to study these things.
Okay. Yeah, I that makes sense. So the only experiment that I've done with particles is when I was in undergrad was just measuring muon decay in a scintillator chamber. So in order for that to occur, what ended up one of the questions that the professor asked us was if the average lifetime is so small compared to how long it takes to get from space, why does it matter? And it's because no matter what initial uh number of particles you start out with, it's always going to follow like the same curve if you start out with all the particles that are hitting the atmosphere versus if you're just starting out with all the particles that are hitting the scintillator. So I've never considered before that if you don't have that many particles like you would see in like a muon decay or something like that, where you're just getting like cosmic rays, or I don't think that cosmic rays is the proper term, but cosmic particles coming into the atmosphere all the time, then it does become important to like track the processes after it decays instead of
Yep.
just when it decays.
Yeah. Some additional difficulty we can have in finding these lambdas is that, when they do decay, one daughter is going to go in one direction and the other daughter is going to go in the other direction. There's a good chance that one or both of these daughters are going to go out the sides of the detector. And if we lose even one of them, we can't find the particle. So there are then some methods that we use to correct for this.
Oh, okay.
Say we call it efficiency corrections. How good is our detector at finding lambdas and cascades and omegas? And it turns out that it's not very efficient, but you
Yeah.
know, we're able to make do regardless.
Yeah. Okay. Nice. So those are all the questions that I have from students, and I think I might have thrown in a couple of questions that were just me as well. But as we come to the end of the interview, I just want to ask the standard end of a job interview question, which is are there any questions that I should have asked?
Um, no, I think we basically managed to cover everything uh that I think students might want to know at this point. Um, yeah,
All right.
no notes.
Yeah, great. Well, thank you very much for uh, agreeing to do this. Everyone in that I interviewed is either currently or previously lived in the same house as me. So
I'm
we're
in his room now.
yeah. So we're just going to knock out the rest of these, and thank you for coming on, and good luck with defending your thesis, which is going to come pretty soon, right?
Yes, hopefully sometime this summer.
Yeah.
So
So
thank you
hopefully,
for having me.
yeah,
This was fun.
yeah, thanks. And then stop.